So here we're going to be looking at two data structures, stacks and queues, and they're both weird because we can use a linked list to implement them, but here we're going to limit the ways in which someone can interact with that sequenced data structure. So a stack is going to be last in, first out. So just like a stack of plates, you always take the top one, and if you added a new one, that's called a push, and then the most recently pushed plate or item, you're going to pop off. That's just the remove operation. And we've looked at stack frames when we were tracing code. So here's the factorial function, and we drew the stack frames for the fac function. So the main method called fac of 5, which called fac of 4, which called fac of 3, which called fac of 2, which called fac of 1, and you can see each of the stack frames. And here it's last in, first out. So the first stack frame to be removed is going to be the n equals 1 case, then the n equals 2, and so on. So again, it's last in, first out. That's the behavior of the stack data structure and of our stack frames. A queue is going to be first in, first out. So this is just the typical line that you might stand in. And instead of getting into a line, the data structure uses the method name in queue typically. And when you eventually are served, it uses the term dequeue. And some common examples are web servers that are processing results or processing requests from different customers, or a print queue. So everybody submits a job to the print queue, and then the print queue puts them in order. First in, first out. Okay, we've talked about interfaces, so what I want you to do now is to try and design an interface for both a stack and a queue. And remember, an interface is just a list of methods that if something implements that interface, it has to provide those methods. And that gives us a common way of interacting with it, and a class can implement multiple interfaces. Okay, so pause here and design the interface for a stack and a queue. Okay, so here's how I designed my stack interface. I had it as a parameterized type, so you can see that E is the variable name I picked for the type of thing that my stack could hold. I added an empty method that returns a boolean, and I added methods pop that removes and returns an object, and push that adds an item, again of type E. And this is a little weird, but it's actually pretty typical where we both add it and we remove that same object. And I think the only reason for this being the common way to do it is, imagine if I'm calling the push method and I have to access some variable. You know, maybe I'm pulling the 30th element from within an array, and I also want to do something with that afterwards. I can put my array access right in the push method and then save it outside. So you can imagine that this allows me to do something that I would have done in 2 lines, save the variable, and then call push on the second line. I can just do that all in 1 line. So I think that's why that's common, to return the same thing you just added. And actually in Java, the stack is implemented as a class and not an interface. So there is a Java class called stack. Your task here was to design an interface, but we can look at the class stack here. And you can see it's got these methods, empty. It's got peek, which doesn't remove the top element, just allows you to have a reference to it. Pop and push that we've talked about. Okay, here's how I designed my queue interface. Again, it's parameterized. I've got an empty, a dequeue, and an inqueue. And actually, in Java, a queue is an interface, and the method names are add and remove. But it's a little more typical to think about a queue as having an inqueue and a dequeue method. Okay, so I have code here that uses a stack, and that stack holds strings. So the first thing I do is I push the numbers 0 through 3 onto the stack, and I just add that int to an empty string to turn it into a string. That's a little bit of a hack, but I add the numbers 0 through 3 to the stack. So I push those onto the stack. Then while the size is greater than 0, so while there are things left on my stack, I call pop and then print the result. And I want you to try and figure out what gets printed in the case of a stack. Before you pause, I've implemented the same thing except with a queue. So I inqueue 0 through 3 in that order, and then while there's still items left, I dequeue them. So I want you to pause it here and think, for the stack version, which we saw here, and the queue version, which we see here, in what order would these numbers be printed? Okay, and I'll keep going. Okay, for my stack, I add 0, and then 1, and then 2, and then 3, and then while size is greater than 0, I'm gonna pop the first thing and I print it, then I pop the next thing and print it, pop the next thing and print it, pop the next thing and print it. So last in, first out. Okay, when I'm working with a queue, I add 0 to my queue, or I in queue 0, then I in queue 1, then I in queue 2, then I in queue 3. And because this is like a traditional line that you might wait in, it's first in, first out. So when I first dequeue something, I dequeue the 0, print it, dequeue the 1, dequeue the 2, dequeue the 3. So I print out 0, 1, 2, 3, whereas with this stack, I printed out 3, 2, 1, 0. Okay, so we could, for representing a stack or a queue, we could use a linked list as the underlying data structure. And here I want you to think about, if you were implementing a stack using a linked list, what would represent the top of the stack? And then what would be the BigO runtime, assuming you have n nodes, so tons and tons of nodes potentially, what would be the BigO runtime of push, so adding something, or pop, removing something? Similarly, I want you to think about, if you were implementing a queue using a linked list, which end would represent the front of the queue? And again, assuming you have n nodes, where n's a variable number and it might be super, super big, what would be the BigO runtime of enqueue or dequeue in that scenario? So do that for both stack and queue, assuming you're using a linked list or something like the list node class that we worked with. And you should pause here, but I'll keep going. Okay, for a stack, I would represent the top of my stack as the head of my list. And remember, when we wrote add to front in list node class, we were able to do that in just 4 steps. So that's going to be a constant number of steps to add a new element. And similarly, when we remove an element from the front, we can do that in a constant number of steps. And the really important thing is this add and remove, they don't rely on how many elements are in the list. Like there could be 3 elements in the list or 1 billion elements in the list, and it doesn't take more steps. That's the real key here. Those ones are in O of 1. So with a queue, I decided that the front of my queue should be the head. So that means that's like the next element to get served, say if they're waiting in line. So in queue, I would have to walk to the very end of the linked list to add an element to the end. So that one would be an O of n, and dequeue would be O of 1, because I can just remove the first thing in my linked list in a constant number of steps. That part doesn't depend upon the length of the list. But I hope that seeing that enqueue depends on the length of the list, I hope you're disappointed. Be like, we've got to be able to do better than that. And sometimes we're going to keep track of redundant information so that we can have performance improvements. So imagine, instead of always having to walk through the whole list to find the last element, what if I just kept an additional reference that always referenced the last list node in my list? Then I could add an element to the end. So you can imagine here, it would point to that last list node. I could add an element to the end just by changing that null to point to my newly added list node. And I could update my reference to point to that newly added list node, the now new last node. So if I just added one more instance variable, instead of the enqueue operation being in O of n, it would be in O of 1. But it could be a pain because I have to keep that additional instance variable up to date. It doesn't add any new functionality. That redundancy just is a bit of an inconvenience and then allows me a performance improvement.